You have spent 3 hours on a service that got slow for no reason you can name, and every fix you tried changed nothing. Your code looks tight. Your 8 cores sit mostly idle. Your users are complaining about a delay nobody on your team can locate, and your manager wants an answer by Tuesday. Sound familiar? So here is a fact about your world that nobody hands you early enough. Almost every expensive thing your program appears to do, it never does itself. Reading a file. Sending a packet. Asking for more memory. Looking at the clock. Your program lacks the power to touch that hardware at all. It asks. Something else acts. And every one of those requests bills you real time you have already lost, in a place your profiler is very good at hiding from you. That bill lands on you whether or not you knew to ask for it. A plain call inside your own code costs you roughly 1 nanosecond. Asking for something across that boundary costs you 200 to 1000 nanoseconds on ordinary hardware, before any useful work at all. So a loop asking 100,000 times has already spent 1/10 of a second on nothing but the asking, and you lose the 10th without ever writing a line that looks slow. Hold that question about where your missing hours went. We will come back to it with a real number, and by that point you will be able to work it out on your own fingers. How much of your afternoon do you think it accounts for? The advice you get will be confident and aimed at the wrong wall. A colleague glances at your flame graph and says, "Give it more threads." Which is wrong, and it costs you a week. More threads puts more of them queuing at one guarded doorway, and you pay the crossing charge more times a second rather than fewer. Will a 9th thread rescue you there? No, and you will lose another afternoon proving it. What I love about this is how thoroughly upside down it feels. The single most guarded operation in your whole machine, the one thing your processor genuinely refuses to let your code do, is also the thing you fire off 100,000 times a second in a loop you wrote without thinking. You would think something that expensive would be hard to reach by accident. It is the easiest thing in the world, and you lose days guessing at your own code instead. So why does nobody warn you? Before I tell you what that crossing really is, guess at something. Your program writes 10,000 short lines to a log file. How many times do you think it asks the operating system to write? 10,000? A few hundred? Hold your guess. Most engineers are off by 4 orders of magnitude, in the direction that flatters the library they trust. That request is called a system call, and the name is grander than the thing. A system call is the one legal way a program asks the operating system to act on its behalf. That is the whole definition. In other words, it is a door. It is the only door. The wall that door sits in is the processor itself, not a policy and not a convention. Modern hardware runs instructions at one of 2 privilege levels, and the level ordinary programs live at simply lacks the instructions that speak to a disk controller or a network card. Nobody at your company chose that arrangement and nobody there can switch it off. Silicon is the enforcement, which is why this is the one performance rule in the stack that no framework gets to opt out of. What you knock with is a number. Not a name, not a symbol, not a string, an integer in a register, and that integer is the index into a table of things the kernel is willing to do. Read is a number. Write is a number. Exit is a number. That is the entire vocabulary of the interface, which I find lovely, and a good deal cruder than any architecture diagram suggests. Where is the elegant abstraction layer everybody talks about? There is not one. It is a numbered list on a wall. And the numbers are never reshuffled. On Linux, the number that meant read has meant read for the whole life of the interface, which is the reason a binary compiled 10 years ago still runs today with no recompile. The term for that promise is a stable application binary interface, which is a lot of words for a promise to leave the rows of a table alone. So what happens when your program asks? First, the library wrapper puts your arguments into specific registers and the call number into one more. Then it executes the trap instruction. The processor switches privilege level, switches to a stack the kernel owns, and saves the registers you were using, because the kernel is about to use them and has to hand them back exactly as it found them. Then the kernel looks up your number in its table, and before it does one useful thing, it checks you. Every pointer you handed over gets validated, because the kernel is not permitted to trust an address a program supplied. Think about what a lie there would buy an attacker: hand over a pointer into the kernel's own memory, ask it to fill that buffer, and you have read secrets that were never yours. So instead of sharing, it copies. Your bytes are copied out of your memory into the kernels on the way in, and then copied back on the way home, so that a forged address buys nothing. Nothing crosses that wall by reference. For a short write, that copy is noise. For a large one, it dominates, and it is the reason sending a file over a socket the naive way moves the same bytes twice for no benefit anybody wanted. Now the arithmetic, and this is the part worth doing out loud. Say a crossing costs 400 nanoseconds all in. Ask once per byte, and 1000 bytes of output costs about 400 microseconds. Then double what you write per crossing and you have that bill, exactly, every time, because the charge is per crossing and not per byte. Double again and have again. That is the whole optimization, and notice that it never once asks you to make anything faster. There is a second charge, and it is not in the register save. The process is simple and unwelcome. Crossing that boundary walks the processor through code and data your program was not using, so what happens is that your caches come back colder than you left them and the buffer that translates addresses gets partly discarded. Is that cost in anybody's benchmark of the call itself? It is not. The measured cost of a crossing is never the crossing alone, it is the crossing plus the noticeably worse behavior of your own code for a while afterwards. I had this model wrong for years, in an expensive direction. I assumed the charge was the privilege switch itself, which is wrong, and believing it left me thinking nothing could be done. Then I measured it properly. Most of what you pay is the checking, the copying, and the cold cache, because those are software, which is why kernel developers have made crossings cheaper over time without touching the processor at all. Which answers the guess I asked you to hold. 10,000 short lines of output never cost 10,000 crossings. The mechanism is a buffer. Your standard library keeps a few thousand bytes in your own memory and only asks the kernel when that buffer fills. So 10,000 lines might cost 200 crossings instead of 10,000. That is why buffered output feels free and unbuffered output feels broken, and it is the same trick Redis leans on at a much larger scale. Redis is the clearest case of a program whose entire performance story is crossing arithmetic. Redis works by holding data in memory and answering in microseconds, so it does almost no work per request. Then nearly everything Redis has ever optimized turns out to be crossings, pipelining many commands into one read, gathering many replies into one write, and running an event loop so one thread serves 10,000 connections with a handful of crossings rather than one per client. There is one more crossing you pay without noticing, and it is the dear one. When your program asks to read from a socket with no data waiting, that request blocks, and what happens next is that your thread hands the processor back to the scheduler. Then waking it later costs another crossing plus a full context switch. Is an idle thread a free thread, then? It is not. It is a thread that gave its seed away and gets charged to take it back. So how would you know any of this, rather than believing a stranger with a microphone? Count them. The procedure is 2 steps. On Linux, run your program under strace with the summary flag, then read the table it prints of every kind of crossing your program made, how many times, and how much wall clock each one consumed. Do it on something you wrote last week. The first time I ran it against a small service, I found a library asking for the clock twice per request, across 60,000 requests a second, for a timestamp already sitting in memory. Nobody profiles what they assume is free. Then do the second measurement, because the first one only tells you the count. Wrap the same hot path in a stopwatch, divide the wall clock by the number of crossings you just counted, and you have the price on your hardware rather than mine. What if the number comes back at 40 nanoseconds instead of 400? Then your kernel is batching something for you and the win you were about to chase is already banked. What if it comes back at 2000? Then you have found something worth a week of your attention, and you found it with 2 commands rather than a rewrite. Then there is the one measurement almost nobody makes, and it is the cheapest of the 3. Count your crossings per unit of useful work rather than per second. A service handling 200 requests a second with 40 crossings each is doing 8,000 crossings a second, and the interesting number is not the 8,000, it is the 40. Because 40 per request is a design decision somebody made, probably by accident, probably in a library, and it is the only one of these 3 figures you can actually change. Redis answers in single digits there. So which of your 40 do you already have in memory? Caveat, batching is not a free lunch, and I would be selling you something if I pretended otherwise. Buffering trades latency for throughput. Every byte you hold back to make a bigger write is a byte your reader cannot see yet, which is why an interactive terminal gives up the win on purpose and flushes on every line. Should you buffer your crash log the same way you buffer a bulk export? You should not. If your buffer is holding the message that would have explained the crash, you will meet that trade the hard way. In practice, whole families of design exist only to lower crossings per unit of work, and they are worth knowing by name. Vectored writes hand over a list of buffers in one crossing instead of one per buffer. Sending a file straight from the page cache to a socket skips the copy into your program entirely, which is a large part of why Kafka moves so much data with so little processor. And the newer submission queue interfaces let you leave a batch of requests in a shared ring and collect the answers later, so the charge is amortized across many operations rather than paid per operation. Jinx and Postgres were both reworked around exactly the arithmetic you just did. Note, whether any of this is worth your Tuesday depends on where your time actually goes, and that is the part you cannot inherit from an article. A service that spends most of its wall clock waiting on one slow database query will not thank you for eliminating a crossing, because no user will ever notice. Unglamorous rule, and it does not bend, measure the count, and only decide afterwards whether the count is your problem. In practice, none of these figures are constants of nature, and here is the twist I find genuinely funny. The mitigations for the speculative execution flaws made crossings measurably dearer, since the kernel now does extra work keeping its address translations apart from yours. On some hardware and some workloads that roughly doubled the cost of a crossing. So a great deal of software got slower on identical silicon, and a security fix quietly raised the price of the one operation this whole episode is about. Did anything warn you? It did not. The kernel cheerfully carried on returning the correct answer, only slower, and told nobody. So be careful with the figures I gave you. 400 nanoseconds is a reasonable order of magnitude, not a measurement of your machine. It depends on your processor, your kernel version, which mitigations are switched on, and which call you make. As far as anyone knows, the only figure that matters is the one you measure on the hardware you actually ship on, and the honest answer is we cannot tell you yours from here. This is where everyone gets it wrong, and it is worth naming. Received wisdom says make the work faster. The work was rarely the problem. What you are lowering is the count of crossings, and folklore about which calls are cheap will not survive contact with your own machine. It is worth remembering how old this idea is and how little of it has moved. Ritchie and Thompson wrote the original small set of numbered calls in the early Unix work, arguing that a tiny, deliberately boring interface was worth more than a rich one. 50 years of hardware later, the shape is identical: one door, one number, one table. Almost nothing else in your stack survived that long unaltered, and 50 years on that is not a limit anybody has needed to lift. So back to the question we parked at the start, about where your missing hours went. The answer is that they went into the asking. Not your loop, not your data structures, not the disk, but the count of times a second your program knocked on a door that charges by the knock. Which leaves you a better question than the one you started with, and you are the only person who can answer it, because it is your machine and your hot path. Ask yourself how many times a second your code crosses that boundary, and how many of those crossings are asking for something you already hold in memory.